In September 2015, a faint ripple passed through Earth. It was smaller than the width of a proton, yet it carried the signature of one of the most violent events in the universe, the collision of two black holes more than 1 billion light-years away. That signal, detected by the Laser Interferometer Gravitational Wave Observatory, confirmed a century-old prediction made by Albert Einstein. It also opened a new way of observing reality through gravitational waves. But beyond the triumph of detection lies a deeper mystery. When two black holes collide and merge, what happens to the information about everything they have consumed? Does it survive, or is it erased forever? Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. If the remaining core is heavy enough, typically more than about 3 times the mass of the Sun, no known force can halt the collapse. The matter compresses into a region where gravity becomes so intense that space-time curves inward without limit. The boundary surrounding this region is called the event horizon. Once anything crosses it, matter, radiation, even light, it cannot escape back into the external universe. For decades, black holes were considered simple objects. According to the no-hair theorem, a black hole can be completely described by only 3 observable properties: mass, electric charge, and angular momentum. All other details about the matter that formed it, or fell into it, appear to be lost. Whether the black hole formed from a spinning star, collapsing gas clouds, or merged neutron stars, once it settles down, only those 3 numbers remain. This simplicity becomes unsettling when quantum mechanics enters the picture. In 1974, Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon allow particle-antiparticle pairs to form spontaneously from vacuum fluctuations. Under certain conditions, one particle falls into the black hole while the other escapes. To a distant observer, the black hole appears to emit radiation. This emission, now called Hawking radiation, causes the black hole to lose mass extremely slowly over time. Given enough time, far longer than the current age of the universe, for stellar mass black holes, the black hole would completely evaporate. Here, the paradox emerges. Hawking radiation is thermal. It depends only on the black hole's mass, charge, and spin, not on the details of what fell inside. If a black hole eventually evaporates entirely, and the radiation contains no information about its internal history, then the information about everything it consumed would be permanently destroyed. In quantum mechanics, that is forbidden. The fundamental equations of quantum theory are unitary, meaning information is preserved. The complete description of a system's quantum state at one time determines its future and past. Destroying information would violate this principle. The collision of 2 black holes intensifies this paradox. When 2 black holes spiral toward each other, they emit gravitational waves, ripples in space-time produced by accelerating masses. As they orbit, they lose energy through this radiation. The orbit shrinks, their speed increases, and the gravitational wave frequency rises in a characteristic chirp. At the moment of merger, the horizons join into a single, highly distorted black hole. It rapidly settles into a stable state by emitting further gravitational waves, a phase known as ring-down. During this entire process, enormous amounts of energy are released as gravitational radiation. In the first detected event, GW 150914, about 3 solar masses were converted directly into gravitational wave energy in a fraction of a second. For that brief moment, the power output exceeded that of all the stars in the observable universe combined. Yet even in this cataclysm, the final black hole obeyed the no-hair theorem. After the turbulence faded, it was defined only by its mass and spin. If each original black hole had previously swallowed vast amounts of matter, stars, gas, possibly even other black holes, the detailed information about those contents seems hidden behind their event horizons. When the 2 merge, their horizons fuse. The internal regions combine in ways not directly observable. Classical general relativity predicts that any irregularities are radiated away, leaving a smooth Kerr black hole. From the outside, nothing reveals the detailed microstructure within. The information paradox forces a confrontation between general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time and treats black holes as geometric objects. Quantum mechanics describes nature in terms of probabilities and wave functions. Each theory has been tested extensively in its own domain, yet when applied together to black holes, they produce tension. One proposed resolution is that information is not lost but subtly encoded in Hawking radiation. While Hawking's original calculations suggested perfectly thermal radiation, later work in quantum gravity implies that small correlations may exist between emitted particles. Over the lifetime of a black hole, these correlations could, in principle, carry away the information. This idea preserves unitarity, but requires modifications to the semi-classical approximation Hawking used. Another influential proposal is the holographic principle. Developed from insights in string theory and black hole thermodynamics, it suggests that all the information contained in a volume of space can be described by degrees of freedom on its boundary. For black holes, this means the information about everything that falls in may be encoded on the event horizon itself in Planck scale quantum states. The entropy of a black hole, given by the Bekenstein-Hawking formula, is proportional not to its volume, but to the area of its horizon. This area law hints that the horizon acts as a storage surface for information. In the context of merging black holes, the holographic perspective implies that when horizons combine, their surface areas and thus their entropies also combine, though not simply by addition. The area of the final horizon is greater than or equal to the sum of the initial areas, consistent with Hawking's area theorem. The increase corresponds to the energy radiated away as gravitational waves. If information is encoded on the horizon, the merger represents a complex reconfiguration of microscopic degrees of freedom rather than destruction. A more radical proposal is black hole complementarity. It suggests that information is both reflected at the horizon and passes through depending on the observer's frame of reference. To a distant observer, information never truly crosses the horizon, but becomes scrambled and re-emitted. To an infalling observer, nothing unusual occurs at the horizon due to the equivalence principle. These two perspectives cannot be compared directly, preventing contradiction. However, in 2012, the firewall argument challenged this view. By analyzing entanglement between Hawking radiation and interior states, physicists argued that preserving unitarity and the equivalence principle simultaneously may be impossible. If information escapes in radiation, the horizon might become a highly energetic region, a firewall, destroying infalling observers. This would overturn the classical expectation that crossing the event horizon is locally uneventful. Gravitational wave astronomy does not yet probe Planck scale physics directly, but it provides constraints. The ring-down phase after a merger is determined by quasi-normal modes, specific vibration frequencies of the final black hole. These frequencies depend only on mass and spin, as predicted by general relativity. So far, observations match the theory with remarkable precision. No deviations have been detected that would suggest exotic structures at the horizon scale, yet the sensitivity of detectors is still limited. Future observatories, such as the space-based LISA mission, aim to measure gravitational waves from supermassive black hole mergers with far greater precision. If subtle echoes or deviations appear in the ring-down signal, they could hint at quantum modifications near the horizon. Some speculative models predict such echoes if the horizon is replaced by a quantum membrane or fuzzball structure, as proposed in certain versions of string theory. The collision of black holes also raises questions about entropy and the arrow of time. Black holes possess enormous entropy compared to ordinary matter of similar mass. When two merge, the total entropy increases, consistent with the second law of thermodynamics. If information is preserved in microscopic correlations, then the apparent loss reflects our inability to track the full quantum state. The paradox may not be that information vanishes, but that it becomes scrambled beyond practical recovery. Recent developments, using the tools of quantum information theory and the ADS-CFT correspondence, have provided new insights. In certain theoretical models, calculations of the Page curve, which tracks the entropy of radiation emitted by an evaporating black hole, show behavior consistent with information preservation. These results suggest that quantum gravity effects restore unitarity, though a complete understanding in realistic spacetime remains incomplete. When two black holes collide, they create a new horizon that conceals whatever lies inside. Classical theory declares the interior causally disconnected from the outside universe. Quantum theory insists that information cannot be destroyed. The merger amplifies the stakes. Vast amounts of hidden data, encoded in matter and fields that once had complex structures, are compressed into an apparently featureless object. The gravitational waves we detect carry precise information about masses, spins, and orbital dynamics, but nothing about the swallowed histories. The paradox endures because it lies at the intersection of our best theories. If information truly disappears, quantum mechanics must be modified. If it does not, general relativity must yield to a deeper quantum description of spacetime. The solution likely requires a fully developed theory of quantum gravity, one that unifies curvature and quantum states into a single framework. Every detected merger adds data to this quest. Each chirp recorded by interferometers is a message from curved spacetime, confirming that black holes exist, that they collide, and that their behavior matches Einstein's equations to extraordinary accuracy. Yet behind the precision lies mystery. The event horizon remains a boundary not only in space but in knowledge. Somewhere within the mathematics describing those mergers is the key to reconciling gravity and quantum theory. Whether information escapes encoded in subtle correlations, resides holographically on horizons, or is preserved through mechanisms not yet conceived, the universe appears unwilling to abandon consistency. The collision of two black holes is not merely an astrophysical event. It is a natural experiment at the limits of physics, where space-time trembles and fundamental principles are tested. The ripples that pass through Earth carry more than evidence of cosmic violence. They carry questions about reality itself. When black holes merge, space-time rings like a struck bell, then settles into silence. What remains hidden behind the horizon may determine whether information is eternal or whether nature permits oblivion. Until quantum gravity is fully understood, the answer remains suspended at the edge of the event horizon, where gravity, quantum theory, and the fate of information converge.